All right. So this is the credibility theory, credibility model session, right? And Michael Barron from American University is the moderator and also the first speaker. So Michael, I'll let you take over.
All right, thank you, Claudia. So what I'm going to talk about is limited fluctuation credibility under uncertain priors. This is joint work with Shengyan Ye. We started when he was undergraduate student at UT Dallas. And at the same time, Bhargat Chattopadhyay was also a faculty at UT Dallas. And you see now, none of us is in Dallas anymore. The research was supported by the Casual Actuarial Society and the Actuarial Foundation, and we are grateful for this nice support. And we're grateful to DePaul for hosting this conference. So since this is the first talk in this credibility section, I'll start with just a few main basic notions, concepts in the credibility theory, and we'll quickly get to my subject. So credibility got a lot of compliments. It's a field that's at least 100 years old. And according to Hickman and Kikas, it's a cornerstone of actuarial science. According to Norberg, the most attractive and important subject in actuarial science. And the whole idea is to combine the real data and the hypothetical data in the optimal way. You know, the Bayesian statistics gives one way to combine them, but actuaries are more flexible. So there is a credibility factor Z that balances the contribution from real data R. Also, you can find it in literature as current observation, subject experience, sample mean, and the rest of the compromise estimator is the hypothetical component, which is not real data, which comes from prior distribution, your subjective beliefs, or often it comes from a bigger group of people, from a risk group that creates your prior distribution. H, hypothetical, also called external information, relative, collective experience, or just the prior. So compromise estimator combines the real data and hypothetical data with this credibility factor between 0 and 1. When Z is 1, that's called full credibility. That means your insured person or insured cohort has enough data, enough insured history, which usually means enough claims. A driver who never committed a single accident, it doesn't have a good driving history. So you need to supplement with prior distribution. A driver with a lot of accidents, that's a good driving history. This driver may have full credibility, enough data. When full credibility cannot be assigned, you will settle with partial credibility. That's any situation with Z less than 1. And you know a number of classical works on this. And the whole actuarial standards of practice, number 25, is just devoted to credibility. For full credibility condition, there are several approaches, Bayesian, Bullman. There is classical credibility approach, also called limited fluctuation credibility. So you will give full 100% credibility, credibility factor 1 to real data if real data is credible enough. Credible means it will not deviate from its expectation by too much. So this fluctuation inequality will hold. It will be within certain relative precision bounds with probability at least 1 minus alpha. Okay, if this is satisfied, then you can award full credibility. According to frequency severity model, very standard model in actuarial science, where the total claim consists of, or the total loss consists of single losses, and there is a Poisson number of losses or claims, and some distribution of losses, gamma, Pareto, typically right skewed distribution. Then you can write out all the steps, and the full credibility condition is that the frequency, this is the Poissonian parameter, frequency lambda of insured events is at least this right-hand side that combines C, this precision coefficient, Z alpha over 2 is the upper quantile, 1.96 or something. Gamma, the coefficient of variation of your losses. So standard deviation divided by the mean of these losses. So this is the limited fluctuation approach. Whenever full credibility cannot be given, then you will give partial credibility. Partial credibility condition means precision with high probability with this factor Z. So if it cannot hold with Z equal 1, then it will hold for some Z, right? For some small Z, this inequality will hold. Okay, and apparently, according to the frequency severity model, the partial credibility can be given if this holds, which means your frequency of insured events is at least the frequency needed for full credibility times Z square. So you can figure out Z by taking the ratio of the real frequency and the full credibility frequency. What's wrong with this approach? Well, nothing wrong. However, it assumes full credibility of the prior. So the data may be fully credible or partially credible. You may have some uncertainty in your data, but this approach assumes no uncertainty, assumes infinite information packed in the prior distribution. And this has been noticed. Mast writes that when you assume the fully credible prior, that means even though it's estimated from past experience, from a relevant risk group, it's also estimated. It's not given to you by an oracle, right, or an angel. The amount of confidence in the prior expectation drives the extent to which the actuary relies on credibility theory. So you do have some confidence in your prior, but it cannot be an infinite confidence. In particular, if the prior mean was obtained as purely a guess, you know, prior can be subjective. Typically, it's based on a larger group of customers, but often it's subjective belief about the distribution parameters. Then the actuary must rely more heavily on the real data if the prior is just a guess, right? This is not built in limited fluctuation credibility approach. Another potential flaw is that the prior may be less than fully credible, says Atkinson in 2019. Since the limited fluctuation approach assumes that the prior has full credibility, it may receive too much weight, more than it deserves. Okay, so this is the first limitation. Several limitations of the classical credibility have been noticed in the literature, and I will talk about two of them. Apparently, you can kill two birds with one stone. Limitation number one is the assumption of error-free, infinitely informative prior distribution. So it's natural how you can cope with this limitation. Introduce some uncertainty. This is what my whole talk is about, introducing uncertainty of your prior distribution. No longer assume that the prior is infinitely known or known with zero variance. Let it also, in a Bayesian way, let it have its own prior, which is a second level prior. You know, it's called hyper prior distribution. So now our augmented model will be this. So the frequency severity model, where the total loss is the random sum of random losses. And when you follow the limited fluctuation approach, this derivation requires asymptotic normality. So you assume you have enough claims for the asymptotic normality. So it would not apply, for example, to life insurance, where if you have a single insured with life insurance, then the number of claims is Bernoulli, right? 0, 1. You cannot claim life insurance more than once. The frequency of claims is Poisson. You have severity parameters, mean, variance, and coefficient of variation. And on top of that, the mean has the prior normal distribution. So the conventional approach, this approach in the literature, assumes no uncertainty in the prior. So according to this, the variance will be 0. variance 0 means no uncertainty. That means the classical approach should follow from our research as a special case when tau is 0. Okay. We may have agreement when the actual expectation of the total loss, which is the average frequency times average loss, equals the prior mean, nu. When they equal, then that will be an agreement, right? But should it always be equal? Well, how about agreement? This is another limitation noted in the literature. We typically assume agreement that the prior mean that comes from our infinitely known prior distribution magically matches the expectation of our total loss. Okay. However, it's noted that heterogeneity exists. So even if you select one group of people who all drive same type two-door sports cars, all married, all have 2 children, for instance, and have no accidents and tickets, still the group will not be homogeneous. Some differences exist within an insured risk group. So heterogeneity exists, people are different. Credibility should depend on the degree of agreement, as always in the world, even beyond actuarial science, right? The more agreement you see, the more credibility is there, right? The more disagreement, the less credibility. Now, the closer the data lean towards homogeneity and comparability with current expectations, the higher the credibility is likely to be. Experience, however, rarely matches contemporary expectations. Note Tyndall and Mast. Experience that you observe rarely matches expectations, which is your prior. Okay, and actuarial standards of practice require that when the actuary uses credibility procedures, they should consider homogeneity of both the subject experience and the relative experience. So what do we mean by agreement? Well, on the left, that's a perfect agreement. So the blue curve is the density of our data. The red is our assumed prior distribution. The mean, maybe they have different variances, but the variances mean completely different things, right? It's amount of uncertainty in the prior mean and amount of uncertainty in your data. Completely different. Don't look at variances. But if they have the same mean, they are in agreement. Here is disagreement on the right when they have different means. So we will work against these 2 limitations. Error-free prior, we deviate from this assumption, and we will handle the problem of disagreement and heterogeneity of our risk groups. Okay, so what happens when we assume that the prior is not infinitely known, if it allows some uncertainty? Well, then we have a sample mean observed, the prior mean assumed. We form an overall compromise estimator, that's the core of credibility, and we will have to work with a compromise estimator that is optimal in some way. In what way will it be optimal? When it has the best precision. So this best precision can be defined differently, and I'm going to offer 3 methods, 3 ways of defining this precision that lead to slightly different understanding of credibility. And in the end, we'll make a conclusion and see how we can choose between the 3. The first method is fluctuation of both real and hypothetical data. This roots from the classical limited fluctuation credibility approach. In fact, the first condition here is precisely the condition for partial credibility, right? The second condition is symmetric, the same condition for the prior distribution, which is no longer assumed completely known. So you have to account for uncertainty in the real data and in the prior. So this approach accounts for uncertainty in the same way. If Z is a credibility factor for the real data, then 1 minus Z is credibility factor for the prior. So similar conditions, maybe with different probabilities, alpha R, alpha H, maybe with different precision coefficients, C and K. But let's say you want to satisfy these 2 conditions. How will it look like? Well, it depends. You see, the whole idea of full and partial credibility conditions depend on the frequency of insured events, right? So when the frequency is sufficiently large, you can have full credibility. What does it mean? Well, I took both probabilities on the right sides to be the same, 0.05, and these are two probabilities that I compute here. So I just computed for a particular case, and you need to choose a credibility factor Z. This is my horizontal axis, credibility factor. That will satisfy both conditions. So both probabilities of large deviations are below 0.05. You have this interval. Moreover, this interval contains 1. So you can choose Z equal 1, and both curves will be below the threshold. So you can have full credibility in this case. Well, suppose lambda is smaller than that, 100. Then you still have some solution here. Any credibility factor between Z1 and Z2 will satisfy both of these inequalities, but the interval no longer contains 1. So full credibility is not possible, neither for real nor for hypothetical data. However, partial credibility exists here. Any factor in between Z1 and Z2 will work. Typically, actuaries will choose Z2. Okay, typically you assign maximum credibility that you can. Okay, well, let's make the frequency even lower. Then this is what happens. You can satisfy one of the inequalities, but not both together. No credibility factor will satisfy both inequalities. And in this case, even partial credibility is not possible. You never had this case in the conventional approach, because when you assume infinitely informative prior, then in the worst case, forget about the data that is noisy and not enough. You can have zero credibility factor. That is, you assign the pure premium and you calculate the full premium solely based on the prior distribution. Okay, so here we can have this case when you don't have enough precision in your prior and in your data, maybe you will have no credibility at all. Well, besides graphs, this approach allows direct computation. So when you solve both inequalities, the system of inequalities, you can derive this interval analytically. So we can look at it. What happens here? The left and right hand of your interval, the interval of possible credibility factors. The solution will exist when lambda n is sufficiently high. So you have sufficiently frequent events, or you have enough insured periods n in your data set. Or there will be a solution when the left side is low, right? And that happens when tau is low. That's the standard deviation of your prior. So when the prior has low standard deviation, that means it is informative. It has enough precision. Well, if both R and H, real and hypothetical data, lack information, then you will have no solution. Then your left-hand side is high and right end is low, and they will not intersect. Okay. High frequency of insured events make the real data more credible because they increase the right end. And when this right hand is more than 1, then the observed data are fully credible. Okay. When tau is 0, I told that's a special case. So when tau is 0, then the left side is negative infinity. So you always have a solution. Either full or partial credibility is always possible because the prior mean will be fully credible with 0 variance. Okay. Second method. Second method is the joint precision of your real data and your prior. It's the same event, the same events here, but instead of bounding the probabilities separately for real and hypothetical data, I bound them jointly. So the probability that either one of them is not credible enough, not precise enough, is bounded by certain probability. Well, you don't have the closed form solution here. You can compute the probability easily using normal distribution, right? But you will not have analytic roots, analytic solutions. You can compute numerically. And you will have this curve, the probability of joint precision. So when the curve is below the threshold point of 5 or alpha, whichever alpha you need, you can choose these credibility factors. Again, when lambda, the frequency is high, you can have full credibility. When it's lower, you have some solution, but not one. The interval does not contain one. If you keep reducing the frequency of events, then at some point you will have no solution. All right. Third method is about the compromise estimate. After all, this is our final product, the compromise estimator. So maybe you should place a precision condition on the result, on the resulting compromise estimator C. So you will give full or partial credibility if with that credibility factor, Z, with this factor, the compromise estimator satisfies the precision, the large deviation condition. So the large deviation should not have probability more than some alpha. Okay. You can also compute this probability, but you cannot solve it for Z analytically. You can solve approximately, but there is always a numerical solution. Nowadays, that's not a problem. It's a nice, smooth function. So this is what you will have. Similar idea, either full or just partial credibility, or when lambda is too low, then you may have no credibility, no solution. Okay. So with this, we can move to the second limitation that steers from this one, the heterogeneity of risk groups. The people in risk groups may differ from each other and may, in particular, may differ from the expectation, from the prior mean. Okay, the heterogeneity risk is defined in this work as heterogeneity within risk groups. That's what we will address now. Due to this heterogeneity, there are insured customers whose expected loss differs from the prior. The actual experience may disagree with the prior, and the prior may be biased for a particular insured. You may have some typical member of the risk group who behaves just like your prior, or you may have some people on the margin of your risk groups who will not agree with the prior expectations. Let's measure the amount of discrepancy. So nu is the prior mean, and lambda theta is the expected value of your loss. So expected frequency times expected loss. This is the standardized amount of disagreement, and this delta gets into the probability of large deviation for your prior, for your hypothetical data. Okay, it will not affect the real data large deviation condition. It will affect pH, but this pH entered our all three methods. So this is how it will affect, how heterogeneity of risk groups will affect our credibility computations. So these different curves correspond to different amounts of discrepancy. Okay, from 0 to etc. So you will have more discrepancy when delta is high. Delta is 0 is a special case of no discrepancy at all. So these three graphs correspond to three methods that I proposed for assigning credibility. And you see that the more discrepancy you have, the less likely you will have a solution, right? You may have solution for low delta, but then when delta increases, there is more disagreement. More disagreement means less credibility. So for a particular case, I calculated an example. What you can see from here, the first 6 cases are delta equals 0. no disagreement, everything agrees. And then you can have full credibility, or when you start reducing lambda here from 600 to 360, then you have less than full, partial credibility. In addition, if you increase sigma, that's the standard deviation of data. So that's the noise. If you increase noise, uncertainty, then you may have no credibility at all. When you have some disagreement, it negatively affects your credibility. So you can have no credibility in the case 3A, where you had pretty high partial credibility in case of agreement. When tau is really low, that compensates for the lack of agreement, because low tau, you remember, means precision, high precision of your prior. And in this case, all your decisions will be based on the prior. And therefore, all three methods will return the same credibility factor. So to conclude, we followed the actuarial standards of practice. Uncertainty is often neglected in the prior distribution, and it's assumed without any error. The actuary should account for both uncertainty in real and in hypothetical data, because this both affects the actuarial decisions. When there is too much uncertainty in both, it's possible that no credibility can be assigned, even partial credibility. Heterogeneity of risk groups also affects credibility, and credibility for a given insured depends on the location of this insured inside the risk group, how close this insured is to the prior mean. Well, the three methods essentially agree. They give pretty close results, but how do you choose between three methods? So the first gives separate conditions. If one component is not credible, maybe you can put full credibility on another component. The other two methods give joint conditions on real and hypothetical data. And therefore, if you lack uncertainty in either real or hypothetical data, maybe the other component can compensate for that, because the condition is joint. They work jointly. So I have some literature that I cited here. This last item is the article that contains all the details on this. It will appear in Variance next month. It's already available on Variance website, or send me email if you would like a copy. Thank you very much. Any questions?
I was wondering if we could leave the questions for the end, since it's a little bit late.
Okay. All right. So then thank you, Claudia. And should I take over the session?
Yes, please.
All right. Then I will serve as moderator. Thank you for the honor. And pleasure to announce our next speaker, Bin Zhou from University of Connecticut. He is currently an assistant professor in the Department of Mathematics there. Bin's prior to this position, he was a postdoc at the University of Washington and the Technical University of Munich in Germany. He obtained his PhD degree from the University of Alberta, Canada in 2015. His main research is stochastic control and optimization with applications in financial mathematics and actuarial science. Today, we're going to hear about Hawkes processes in dynamic credibility. Bin.
Michael, yeah, thank you, Michael, for this kind introduction. Indeed, today I'm going to talk about something I've been thinking of, in with former PhD student Hing-Chang Zhang. He graduated from UConn right now. He's at Simon Fraser. Now let's get started. So here is a quick review of the standard risk model, which Michael did an excellent job of reviewing it anyway. So I only mentioned that in this talk, we will be mainly focused on the claim frequency. In other words, we will only look at N instead of the aggregate. So now let's get a quick notation, sort it out. So here I use NT to denote the claim frequency in the Tth year. Okay, so it's not accumulative; it's only for a single period. And here, let's say just the one period is 1 year. Okay. So under the standard, Cramer-Lundberg model, we have a Poisson distribution, for the number of claims in each year, and they are independent. So that is something we're going to argue against, and we are trying to propose a new framework to somehow get away from this independent assumption. Of course, we know, right? We assume independency, not because it is the case, but because it makes everything easy to handle. Okay. Of course, for the Poisson part, you can apply any reasonable discrete distribution such as negative binomial or geometric. Those are very common in actuarial science. I already mentioned claim frequencies are hardly independent, right? So here is a quick case. Let's say, right? Suppose you own a fabulous Porsche. So let's say Michael owns a Porsche, right? It's 911 GT3 RS. Is very expensive, right? It's probably versus 2 of my houses. Okay, so it's a very expensive car. In case you were involved in a car crash, and of course no one was injured, the company, your insurance company, had to pay $50,000. So what would you expect on your next year's premium, or rather 6 months premium in the US, and why? Right? We know for sure that you're going to see a huge jump or huge rise, in your premium, right? Because of this expensive car crash. Okay, the reason is simple, right? If you have studied credibility, or if you just saw Michael's slides, you will know that it's very likely that under a reasonable credibility model, your prediction for next year is let's say linear combination, right, between what you know empirically and what you know from the model. So if there is something happening, it's going to move your credit rating up, right? So they are not independent, right? This is a quick example to show that independency is likely, not going to work. Okay. So how are you going to address that? Okay. Here, let's take a look at a standard approach, or maybe the standard approach, right? So what people usually do in actuarial science is they introduce observable covariates, okay, and hoping that by isolating those covariates, they are independent. So all those n's, they are not independent, but conditional on those observable covariates, they are independent. So basically, you try to isolate, those factors that could explain some kind of dependency, right? Once you isolate them, they are independent. So they are conditionally independent. And then, you can apply any reasonable statistical methods to estimate the parameters. Usually, you still do Poisson, right? And then there's only one parameter of the intensity, which is given by this exponential form, right? And then you can apply any methods to estimate gamma. Once you know gamma, it's solved, right? And further, you can even incorporate random effects, meaning, there could be possibly, different year effects. So you can further replace this intensity by this product. So here, theta is something random, okay? It brings additional layer of randomness into the model, right? So when theta is 1, is the standard approach, right? When theta is random, when theta follows some prior distribution, you have additional level of randomness that helps, explain what we see in real data. Of course, you're going to assume some prior distribution on theta in order to get things to work, right? There's a large body of literature on this line of work, and I here only list the very, very few. Okay. There are, of course, many questions we can ask, right, on this standard approach. For instance, what covariates should be included in the study, right? I mean, some may be better than others, right? And you might miss some important ones, right? If you miss some important ones, your assumption of independency may still be under attack, right? And further, if you apply random effects, you need some knowledge on the prior distribution. And obviously that's, you have to guess right? Or based on your knowledge. But again, there's no uniformly accepted way to determine what would be the best one to choose, right? So here we're going to look at this from a completely different angle. Okay, I call it alternatives. I'm not sure whether it's good or much better, but anyway, it's alternative. So what we start is not look at n, we look at the cumulative. So we start with the process. We start with the stochastic process, C, okay? This is cumulative in the sense that any number of, claims would be the difference, between CT and CT minus 1. That's why I call the process C the cumulative claim frequency, which means CT is not from T minus 1 to T, but rather from 0 to T. So it's cumulative, okay? I try to model this process. Once we have this model, well, NT is trivial, right? So here our starting point is to model the cumulative claim frequency. And hopefully we can come up with a model that could capture some of the properties that are desirable, that we want, okay? And here, obviously, you can tell from the title, we're going to apply Hawkes process, okay? And a special Hawkes process with exponential kernel, which we're going to review. This approach actually opens an entire door for new alternatives, right? Hawkes process is a point process. You can apply any general point process, of your interest, right? There are so many choices, right? Other than Hawkes, okay? So it opens the entire door. And even for Hawkes, you can apply any kernel you want. Here we only apply exponential. You don't have to limit to exponential kernel, of course, right? So that's why I mentioned there's a lot you can be possibly done along this direction. So now let's take a look at the model. So let's begin with a quick review of Hawkes. You can think Hawkes process as a generalization of Poisson. Right? For Poisson process, your intensity is either constant, which is mostly the case, or homogeneous function. So here for Hawkes process, the intensity itself is stochastic. So sometimes people call this, doubly stochastic processes, right? Because the point process obviously is stochastic, and the intensity is also stochastic. Moreover, it is unobservable. Okay, you don't directly see the true intensity. It has to be estimated. So from this, you can easily see that the intensity is similar to how you define Poisson process, right? Except here, you have to be slightly careful with the conditional expectation. Other than that, you can really relate it to Poisson, right? So even you don't understand Hawkes at all, and it's a generalization of Poisson. You can think of that way, right? With more complicated intensity. Here we usually model the stochastic intensity in this way. So first, there are two components. The integrand is what we call the kernel function. So what kernel function does is to measure the impact of a jump on intensity, okay? And obviously here is the point process itself. So whenever there is a jump from the underlying point process, your intensity will change, will get a jump as well, okay? And this kernel function captures how over time the previous jump is going to impact in the future intensity, right? By exponential, it gradually decays, right? Somehow, it's good for actuarial science because that's usually what we see, right? So if you happen to be involved in an accident, the impact is much stronger in the following year, right? And then it gradually reduces. After a certain number of years, the impact is gone. Let's say 5 years, it's no longer impacting anything. So exponential decay is somehow okay once you have a nice parameter, right? So here is what I call the exponential parameter, exponential kernel. Obviously, it's an exponential function. So if you ignore this beta, it's simply, exponential. Here we have two parameters. Alpha is the speed of decaying, how fast you want the impact to vanish. And beta is the jump size. Whenever there's a jump of, well, let's say whenever you see a claim, how much you think the rating will go up. So beta measures the increment of the rating, okay? Obviously it should be positive, okay? A good thing of exponential kernel is that we can write down the dynamics of the stochastic intensity. It follows a mean diversion. So this is mean diversion, which means between any jump. So here is one jump, here is the second jump. In between, it mean diverts. So whenever there's a jump, it will go up, right? And then in between, let's say this is the long-term level. You are still below the long-term level, while you are going to gradually go up, right? Trying to match to the historical level until the next time you jump. So when you jump and when you are above, you're going to go down. You know, that's the mean diverting, right? And it makes perfect sense, you know, to the application in actual science. So now we here's, you know, obvious from the from this, right, from the dynamics, right. So if you have dimension 1, you can see that whenever there's a jump, your intensity goes up by beta. When you have higher dimension, let's say, you know, an insurance company has multi-line business, line 1 can affect line 2, okay, when there's a jump, right. That's very common in financial markets, right. So whenever there's a jump, let's say Apple, it will spill over to Microsoft, to other tech companies, right? So maybe in insurance, you want to model the same kind of effect, you can do this. This is what we call the clustering effect. Okay. Now let's move on to the actual model. What we want to do is this part is, well, not surprising, except now there are more mathematics involved. So FT is the information, what you can observe. Okay, conditioning on the current information, your best estimate for the next, your model for the next period is going to be a Poisson. Okay, we like Poisson for claim frequency for sure, but the real thing is the intensity. Intensity is a lot more complicated. We know from the definition of the Hawks, our intensity is going to be stochastic. Okay, so what we do is right now you know everything at little t. You are trying to predict for the next time period, okay? And your intensity between t and t plus 1 is stochastic. What you are going to do when you don't know for sure about the future, right? Your probability cost says that you should apply conditional expectation, right? That is the best estimate if you don't know the future and you want to know what would be the best estimate for the intensity, actually the aggregate intensity, right? So that's why we need to integrate, well, actually from t to t plus 1, right? Because here is t plus u, so it's from little t to t plus 1. We want to know what would be the aggregate intensity over the next period, and we do conditional expectation, right? So far, things are, I think, are understandable, right? Not completely, you know, complicated, right? So our job is to come up with some estimate for this intensity, right? Because it's a Poisson model. Once you have an estimate, the estimate would be your credibility, right? Because it's a Poisson, okay? So our next job is to estimate this capital gamma or capital lambda, you know, for the next period, okay? We need to make some assumptions. This is, you know, hardly assumption because when you have insurance data, it usually comes in discrete times, right? Does not come continuous, at least for most of the free data, right? You don't know when a claim happens. So this is somehow reasonable. This is what we make to make sure we can get a nice result. This is a result. After some mathematics, you are able to derive an explicit formula for the intensity, okay? And here, well, alpha and beta come from the Hawks process, and this tau j is the arrival time of the j's claim. In the numerical analysis, we simply assume all claims happen in the middle of the year. Well, of course, it's a strong assumption because we don't exactly know. If we know, that would be better. The only one would be this mu t. Mu t, we also have this nice formula, okay? Actually, more standard way is to do this. Right? From the standard approach, introduce some covariates and apply GOM or log likelihood to estimate this OT, this mu t. This is what we do. But we do have the theoretical expression down here. So everything is explicit. We have the result. So now let's move on to mention what we have so far. since this is still an ongoing project, nothing is finalized. I show you what we have. So data, what do we have for the data? Well, this is well known in actuarial science, right? This is actually from the book of Jet, right? This is well known in any data analytics. So it is from Wisconsin Local Government Property Insurance. It's somehow okay, you know, for this purpose, because it's it has all the claim information for the it serves as a good example for multi-line insurance, you know, data set. So, and it's publicly available. Everybody can, you know, if they have the codes, they can always check. I think that is something more and more journals want. You know, once you publish, they want your results to be replicable. So objective, what we want to do is we want to compare our dynamic credibility model to the benchmark model. The benchmark is actually static. I will mention in a minute what I mean by dynamic. So the static credibility, well, they do consider the possible dependency, okay? However, the weight is constant, or the impact is constant. It doesn't matter when this claim happens. It's a constant impact. However, in our model, it's dynamic, right? It's exponential decay. So if the arrival time of the claim is relatively new to the next period, it has higher impact, right? To me, it makes intuitive sense, right? So that's why we call our model dynamic, right? As time moves forward, the impact gets smaller and smaller, eventually vanishes. So that's why the dynamic model is not static. So now let's do comparison. We pick some criterion. Those are really well used, right? So RMSE and MAE. The one is the square root of the mean, the square root of the square, the square, and then we have the absolute error, and both are well used in the analysis. We try to come up with a result. Of course, this is the real observed, right? This is your best estimate. Depending on the model, right? For the static one, this is the expression. For our case, it's relatively simple. Well, in mathematical expression, simple. But how to get this is a lot more complicated, right? We have already seen from the previous slide what we have for this capitalized lambda, right? So we can do the analysis. Here's the result. Let's say for this particular data set, our dynamic framework is much better. Right? So, you know, if you do a comparison, it did much better. Right? However, we cannot, you know, conclude that we are certainly better for all data sets. At least for the one we picked, our framework works much better than the standard static one. Okay. The final slide is about the dynamic versus static. This picture says everything, right? So the orange one is the static model. So here we consider a very simple example. We consider one policy with exactly one claim in the last 5 years. So it can be in any of the 5 years. If you apply the static model, the impact on the next year is the same. It doesn't matter whether the accident occurred in, so here. So we want to predict the 6th year, right? So the data we have is for the previous 5 years. It doesn't matter whether it's the 5th year or the 1st year. The impact is the same for the static model. So that's why it's the same, right? In the credibility model, the impact is the same. That's something we don't want to see, right? For our dynamic model, this is year 5. This is year 4. This is year 3. So the horizontal axis is the time to the next period. So that's why the 1 is the most recent one, okay? So it's decreasing, right? And makes intuitive sense and probably closer to reality, right? So if an accident happened in the most recent year, it has a lot higher impact on the 6 years credibility rating than the same accident in the 1st year. So that is the takeaway message from this model is the impact should gradually reduce and eventually vanishes, right? So that's our takeout message. One thing I really want to mention is from the Wisconsin data set, we don't know exactly the time of the claim. So we have to make this assumption. So here I maybe ask the audience, if you know some data set that has exactly the arrival time, please feel free to let me know. We're going to redo the numerical analysis because we need to know exactly the arrival time, but we don't know, from the data set we choose. And we picked exponential kernel. That's because of its nice analytical property. You may argue some other kernels are better. Actually, in SESMAC or in Earthquake modeling, Power kernel is popular, and they found Power kernel to fit the data better. But when you apply Power kernel, you don't have nice dynamics. It destroys the joint Markovian property. But many of you are better in mathematics. Maybe you can handle that. So once in that, I think I should conclude here. And in case you have a quick question or something, feel free to ask.
Questions? Comments? Remarks? There is
how flexible is our model? What range of dependency can capture? It can do anything. Well, maybe not anything, but there are two parameters, alpha and beta. Those should be calibrated, according to data. So it's quite flexible. And the good thing of Hawk's process is it easily generalizes to higher dimension. That's another thing I want to mention. When you do a standard modeling, let's say you apply Poisson for one line, how are you going to do for the other line, right? How are you going to handle the possible dependency, between line 1 and line 2? When you apply a Hawk's process, it can be naturally multi-dimensional, right? The dependency would be captured by the matrix, by the joint matrix, right? If you have higher dimension, this is the impact of line 1 on line 2. This is the impact of line 2 on line 1, right? So the dependency could be relatively easily captured when you have a naturally multi-dimensional process. That's another good thing of Hawk's process.
Great. Any other questions? Thank you very much, Bin.
Yeah.
So you can.
So let me stop sharing and pass the floor to Him-Chan.
Thank you. So our next speaker is Him-Chan Jeong. He is an assistant professor in the Department of Statistics and Actuarial Science at Simon Fraser University in British Columbia in Canada. Him-Chan is a fellow of the Society of Actuaries. He holds PhD from Dean's University of Connecticut. He has been actively involved in teaching and conducting research in actuarial science for several years already. In recognition for his academic achievements and excellence, he has been awarded the James Hickman Scholarship from SOA recently in 2018-20. His current research interests are in predictive modeling for the rate making and reserving of property and casualty insurance. And today he's talking about approximation of zero-inflated Poisson credibility premium via variational Bayes. Him-Chan?
Thank you for your kind introduction, Michael. So I'm Him-Chan from Simon Fraser University. So this is a joint work with Min Kim, a PhD student at Michigan State University, and Professor Deepak Dey at UConn. So, okay, let's start with the introduction. So here I also focus on the claim frequency. So N sub IT denote the number of action for policyholder I. So I means the index for the insured driver or policyholder, and T means the index for time, year. So we have number of claims for the person for the year, exposure, and available covariate. And then traditionally we have used Poisson distribution as an industry benchmark, so that N given X follows Poisson distribution with possible exposure adjustment. But considering the longitudinal property, or considering the situation that we observe the same person denoted by index I for many years, right? Over and over. So we could consider incorporating random effects as follows. So here, theta I captures possible deviation or unobserved heterogeneity. And then we assume that theta I follows the common prior distribution. But as we observe more and more previous data, we can update the common prior distribution for each person. So that each person ends up, each person's claim ends up with distinctive posterior distribution for theta I. So it gives one example why we may need to consider unobserved heterogeneity in risk. So as Michael said in previous talk, so suppose we have two hypothetical policyholders. So they are identical in terms of observed covariate, right? The same gender, the same age, the same vehicle size. We do see that, and they have two types of claim. And then we will see policyholder A had much favorable claim experience compared to policyholder B, right? So we have to conclude that there must be something that we couldn't observe out of those characteristics. And then if these are the all characteristics that are observable, then we have to incorporate such kind of unobserved heterogeneity in a way. So that's why we can consider random effects. And the random effects model is good connection with credibility and bonus model system. So this is the called traditional Poisson gamma model. So basically we compute Bayesian credibility premium. So assume that the prior distribution follows Poisson distribution. So R controls the amount of uncertainty. So if R is large, then we have less uncertainty. If R is small, then we have more uncertainty. So this is a posterior density. After you update the prior density with the observed information, it still ends up with gamma distribution because they are conjugate. And the predictive distribution of new year, even the previous year's claim, follows negative binomial distribution. And then the predictive premium is given in this way. So new for the new year. So new I plus t plus 1 means the prior premium due to the observable characteristic in the new year. And this ratio accounts for the ratio of actual claim to the expected claim, right? So if there were more actual claims than the expected claims, then we would give surcharge more than 100%. But if the expected claim were more than the actual claim, then we would give discount for that policyholder. So this is the intuitive meaning of traditional Poisson gamma model. So it is good to interpret, good to estimate, and easy to obtain the closed form. But we still have some possible issues in the traditional model. So here, the first one is possibility of zero inflation in claim frequency, right? So if we observe claim data, most of the claim data shows that 90% of claim are 0 and 9% of claim are 1 and only 1% consists of 2 or more. So we do see significant zero inflation when in any claim frequency. And also you can consider the impact of past claims according to their age, but the second one was covered by Bean's talk. So I'm gonna focus on the first issue, possibility of zero inflation in claim frequency. And how can we incorporate this aspect into the credibility premium? So here, to incorporate possible zero inflation, we assume that n sub it follows. Now, zero inflated Poisson looks like. So now we inflate the probability as 0. So this pi it controls the inflation. So if pi equals 0, then it reduces to just traditional Poisson model. And suppose we use the same gamma prior here, then we can obtain the closed form of posterior density. Because, so maybe we can use MCMC to find the posterior samples. But it's quite time consuming because, so here we have prior for each person, right? So which means we have to estimate the posterior mean for each policyholder, but usually a insurance claim portfolio consists of millions of policyholders. So if we apply MCMC for each person, so it's scaled to the time, so we do super time consuming, so may not be appropriate in practice. So we might need a better way to approximate the true posterior density or true posterior expectation. So here our approach is to use variational base. So we assume that the variational family, that we find a variational density that is closest to the true total posterior. So we minimize the Colbert-Liebler divergence between the true posterior and distribution in the variational family. So in variational base, the choice of variational family Q is quite important, right? So it shouldn't be too broad nor narrow. So you specify the variational family in this fashion. So Q is specified in this way. So Q, we choose Q from that has such shape. So the shape parameter and scale parameter are controlled by observed claim and expected zero inflation, expected frequency, and lambda Q parameter, dispersion parameter. So the rationing of such choice is this. So if you use such family, then expectation of theta under that variational distribution is given in this fashion. So if we have infinitely many observations of N and V, N and nu, then the expectation of theta under the variational distribution Q would converge to the maximum aspect of theta. And also if pi is 0, then the variational family just reduces to the traditional conjugate posterior. So this is our rationale to choose the variational family in this fashion. So we define elbow in this fashion, and we use stochastic gradient descent to iteratively update the elbow and find the optimal parameter, variational parameter. And here is simulation study. So we want to assess the applicability of the proposed method. So here we generate a data that consists of 5,000 policyholders and 6 years. So we assume that N follows zero inflated Poisson model, and theta follows gamma prior, and we have one covariate. So we use 5 years data to train the benchmark models, and the 6th year are used for auto-sample validation. So we consider 6 models. So the first 2 models are without zero inflation. The first one, Nye Poisson, so no credibility at all. We just used the observable characteristic without zero inflation. And the second one is Poisson gamma model. So you consider both static credibility and the prior information or observable information for the next year. And we have 4 models with zero inflation. First one is Nye, zero inflation, so no credibility at all. And this is a proposed model. So the proposed method that considers both zero inflation and credibility factors via variational family. And base premium. So base premium means we approximate the posterior mean of theta using the posterior samples via MCMC. The true model. So here true means we assume the perfect knowledge on the random effect. So the true random effect is known, assumed to be known, but the other fixed effects are still estimated. But as we see, true model is not available in practice. So it is just given for comparison. And to assess the prediction performance, we use root mean square error and mean absolute error. And we have 6 methods, and one can expect that the true method should be the best, right? In terms of root mean square error and mean absolute error, true method is the best. But the variational based method, the proposed one, is compared to the other method is outperforming the first 3 and also even comparable to Bayes method. So Bayes method that uses posterior samples via MCMC. The problem is that although their prediction performances are comparable, but the computation time for the Bayes method with MCMC is quite time consuming. So in this way, we can argue that our proposed method can be a good approximation of the true Bayes premium with considerably less computation time compared to usual MCMC. And here we give data analysis. So for the empirical analysis, we use also LGPI-F dataset. And although it contains multiple lines of insurance, we only use inland marine claim information. So these are the observable covariates that we have used. And first, before we apply zero inflation model, we do the test whether there is indeed zero inflation or not. So according to Vandenbroek, we tested the presence of zero inflation. And according to the test statistic, the value of the test statistic was 1.967, so that the corresponding p-value is 0.08. So it tells us that there is not negligible level of over dispersion or zero inflation in IM claim frequency. So and as I mentioned, we have 2 schemes basically, whether we include zero inflation or not, right? So for the model without zero inflation, we estimate beta. And for models with zero inflation, we estimate both alpha and beta. And as shown in the following table, the proposed model shows the best performance. So it's compared to the other method. So the root mean square error and mean absolute error were the best in the variational based method, and also the computation time was much less than the Bayes method that utilizes usual MCMC. So these are concluding remarks. So the proposed method provides us a way to consider both unobserved heterogeneity and risk, as well as possible zero inflation via the use of variational based, which ends up with analytic form of posterior premium. And also an empirical analysis with LGPIF dataset shows us the proposed model performs traditional benchmarks in terms of out-of-sample validation and computational time. Thank you so much for your attention.
Thank you, John. Any questions? We have a few minutes for questions. I have one, maybe it's a very minor detail. In your Poisson gamma modeling, I think you used gamma distribution whose 2 parameters are equal to each other, the shape parameter and the frequency. Does it mean something?
Yeah, it's a really good question. So
yeah, like here you have gamma RR, right?
Yeah, RR. That means they expect the prior mean of theta is 1. So a priori we do not discriminate any person. So a priori we don't see any impact of unobserved heterogeneity, right? Because we didn't observe anything about the unobserved heterogeneity. So at first, this means like the proportion, the credibility factor, initial credibility factor. So it should be 100% if you're a new customer to the company. But after we update the prior density with the observer claim, then the posterior posterior expectation of theta could be more than 1 or less than 1.
Mhm.
So it gives that meaning, or statistically, it gives us identifiability issue, because we have to estimate R and also the fixed parameters, the parameter beta that are associated with nu. So statistically, it gives identifiability issue, and in terms of insurance perspective, it's comparable to the initial credibility factor, which should be 100%.
Mhm. Okay, thank you. Questions to Him-chan? Or questions to any of the previous speakers? Because we have a few minutes.
Hey, Michael, I do have one quick question on your presentation. I think in the last method, you are trying to regulate the credibility between the expectation of X. What if your information on the expectation of X is not accurate? You know, because the model is to say, you know, the kind of, you know, an implicit assumption that the expectation of X, it's something you are trying to get close to. And if that information is incorrect, you might be doing the incorrect thing. So that's my concern there.
Yes, so thank you for the question. So expectation of X can be estimated because we observe losses, and we are assuming that the pattern that we observed will continue during the next insured period, right? So we estimate the expected frequency, and we estimate the parameters of the loss distribution, the loss models. It's just estimated, right? As opposed to the prior distribution that we may estimate from past experience, from bigger groups, or may just subjectively assume a prior distribution. So the prior may be wrong if it's based on our assumption. Like Him-chan assumes inflated Poisson prior distribution of the distribution of the frequency, but maybe it's something else. So assumptions may be wrong. The parameters of your real data, like lambda and theta, are estimated. So you will not be wrong by estimating, but the assumption is that next year it will be the same. The assumption that may be right or may be wrong. Of course, you can you can account for general trends, everything that happens in your data, but if a new strain of coronavirus comes next year, you're not accounting for that, right? So in that sense, you may have an error in your real data, right?
Yeah, indeed. Because, you know, I'm more from the math finance side, and usually when we speak for model uncertainty, we're going to introduce a family of models. You know, sometimes even model free, and the good thing from that part is you get a rather general result. The bad thing is you probably don't see anything. You prove, you know, some things, but you don't get a nice result. So, you know, what I'm thinking is, have you seen any research that when you introduce a prior, it's not a prior distribution, but rather a family of distributions? And when you do any regularization, you know, you try to regularize from the family, trying to use, let's say, some training data to pick one rather than, you know, pre-chose one. So do you happen to know any research from that?
Yes, so there is some research, Bayesian research. There is a whole area called Bayesian robustness. Maybe you heard it was developed the first half of 1980s.
Okay.
If you know the classical book by James Berger, he's one of the founders of Bayesian robustness. Between his first and second editions, that's the main difference. the
Oh.
Bayesian robustness,
Bayesian.
where exactly what you propose, instead of one prior distribution, you assume a family of priors. And what is robust? Within this family, you find one base rule. In our case, it will probably be a credibility compromise estimator that performs reasonably well in the whole class.
Yeah,
So
that's
it may
true.
not be optimal for a particular prior distribution,
Mhm.
but it's conservatively optimal over the entire class of prior distributions.
Yeah.
There are some interesting results there. You can assume that you know a prior up to some error that is called epsilon contaminated class, that you allow some contamination of your prior.
Yeah, exactly.
Or you may think of the whole class of prior distributions where hyperparameter has its own distribution, and you're entering hierarchical base then.
Yeah.
That's a nice comment. And there is this area Bayesian robustness, which does not assume that you know one prior distribution. It allows a family of priors.
Okay. Good. Yeah. Thanks for that. Thanks for that, Michael.
Okay. Thank you, Bin.
I have a question for Bin's talk.
Sure.
So I just make sure if I understand correctly. Anyway, you want to estimate, for example, like the number of claims, let's say in the t+1 year, right? Given the data from up to t years, right? And then you don't know exactly when the claims happen between time t and t+1, right? So you assume that the sigma field, right, at time t plus u would be the same as the one at time t, right, for fractional u, right? So, but then at the end, right, at the end you make some comments saying that you still want to know exactly when the claim occurs, right? You don't know when the claim occurs, so you assume they occur in the middle of the year, and then at the end you say you still hope to know when the claim exactly occurred. But if you know when exactly the claim occurred, do you need to modify your analysis because of the sigma field, because you do know more about
for that we don't, because for the capitalized lambda, we conditional on small t, so we conditional on small t, so we don't even need the assumption that the sigma field t plus u equals the sigma field at t, because we condition on small t. But if you know the past, I'm not sure how much that will help, because the real approximation we use is simply to take the arrival time to be t plus half for each year. So that's the assumption we need. And for the information, probably we don't need to make that assumption. Is the first one, the mu t part. We do need a little bit assumption. Yeah. But thanks for that. Yeah.
All right.
Yeah,
so we'll have more time for questions and answers in the end of the session. And meanwhile, it's my pleasure to introduce our next speaker, Eric Cheung from University of New Southern Wales. That's in Sydney, Australia. So it's already Saturday morning there, right? And Eric is an associate professor at the School of Risk and Actuarial Studies. His research interests include insurance risk theory, ruin theory, aggregate claims analysis, queuing theory, and stochastic processes. And he has published more than 40 papers in these areas. He is an associate of the Society of Actuaries, and he has also been an associate editor of Insurance, Mathematics and Economics since 2019. Today, he's talking about Bayesian credibility and the bivariate conjugate prior on frequency and severity. Eric.
Thank you, Michael, for the very nice introduction. So can you see my slide, the first page? Okay, that's great. Yeah, so actually, it's the first time I give a talk in the ARC, although as a student, I attended it like, I think 15 years ago in 2006. So I think I would like to thank the organizer for this very successful conference that is very well organized. I certainly understand, after organizing the IME, I certainly understand that it's not easy to accommodate lots of requests from the speakers, and then accommodating the time zone and so on, and putting the talks in the parallel section. So thanks, I would like to thank the organizer for that. And today I'll talk about Bayesian credibility under the dependence of the prior distribution. So this is joint work with Wei Hong Lee, Rosie Oh, and J.K. Wu. So I I'm fortunate to be the last speaker because I don't think I need to introduce what credibility is. So I will just browse through the first few slides fairly quickly. So this is the outline of my talk. In the first part, I will introduce the model fairly quickly, and then I will move on to some general results with regards to a bivariate posterior. I will introduce the bivariate prior distribution, and then which will lead to a nice result with regards to a bivariate posterior. And then I will talk about some general results on the Bayesian premium as well. And our formulation would be general at the beginning, and then we will move on to more specific examples where we would have more explicit results, such as in the case of bivariate mixed air-length prior, where I will not only talk about the things like Bayesian premium, but I will also talk about specifically the predictive distribution of the aggregate claims and the number of claims, and also some higher moments or joint moments. And then if time permits, I will move on to talk about briefly 3 more additional examples of bivariate prior that can lead to nice results. And then I will move on to some numerical example. So we know that in credibility, of course, if you are in this section, you must already know that, right? Our goal would be to project the next year's premium charged to a policyholder given his or her claim history. And of course, there are some classic textbooks about it. And in the traditional credibility context, typically independence is assumed between the claim number and the claim amount. Then in particular, it was typically assumed that the risk profile, if we have if we have the unknown risk profile, or in some other talks, it's called the random effect. So if you assume there's a random effect corresponding to the claim number and another random effect corresponding to the claim amount, the classical credibility assumes that these risk profiles are typically independent. And then the Bayesian premium, when you look at the Bayesian premium for the aggregate loss, then in this case, under independence, the Bayesian premium would be just the so-called Bayesian premium for the claim number multiplied by the Bayesian premium for the individual claim amount. Okay, so that is the classical case. Okay, but of course, we know that I think as been mentioned, the independence is too good to be true, right? We make that assumption, right, for in order for the results to be trackable and to get nice formulas, for example. So recently, there are a couple, quite a number of works trying to incorporate dependence either in a non-credibility context or credibility context. Okay, so I'll just refer you to these papers. Okay, so actually, this paper that I'm presenting just appeared in IME. So I'll refer you to the paper for the details. So I would just like to focus on the ideas in this talk. Okay, so this is our proposed model. So we would look into, for example, a given contract. Okay, assume that we have focused on a given contract or a given policy or given policy holder. Okay, so we will use this X substitute by H and sigma to denote the aggregate claim amount for this policy in the year H. Okay, so here this is represented as an aggregate. Okay, so NH would be the number of claims in year X for this policy, and then X of HL would be the amount of the L's claim in year H. Okay, so this is the notation for a given contract. Okay, so we assume that we have T years of claim history for this guy. Okay, so the claim history is collected in this capital N and capital X. Okay, there's a history of claim number and the individual claim amount. And then we assume that, okay, or notationally, we assume that we have the lambda and theta, that these are the risk profiles or the random effect corresponding to the claim numbers and the claim amount respectively. So we will assume that, okay, the claim number, okay, N of H across different H, okay, across different years. So conditional on the lambda, okay, the claim number would have PMF, okay, we have this PMF F and given lambda. Okay, so the lambda will basically control the N. Okay, the lambda only affects the claim number. On the other hand, the theta will only affect the claim amount x. Okay, so the x will be IID conditional on the theta, and then the PDF or PMF would be f of x given theta. So here we would like to, so in the classical sense, the lambda and theta are typically assumed to be independent. So we want to incorporate dependence here. Okay, so here, so we would like to assume that because we would like to obtain some nice results with regards to the conjugate prior. Okay, so we know that in the classical univariate case where we assume independence between claim numbers and claim severity, the use of the linear exponential family will lead to the nice results if we use the right conjugate prior. So we would assume that the likelihood, okay, of n given lambda itself follows the exponential formula with this standard notation in the loss models book by Klopman et al., for example. And then also we assume that the individual claim amount, the PDF or the PMF, okay, also follow the linear exponential family. Okay, so these are standard. Okay, so now we know that from the standard results, okay, we know that, okay, we can have if you ignore the dependence for a moment, okay, if we just focus on, for example, the claim number first, okay, we know that this pi, okay, this pi for each I, okay, for each subscript I here, this pi will actually be a conjugate to the claim number. Okay, and note that in the PMF of the claim number, we have things like P1, the function P1, and then R1, okay, and then we have the Q1 as well. Okay, so here in the conjugate prior, okay, we have the same Q, we have the same R as well, and then we know that the C in the bottom is just a normalizing constant, and then we know that for each I, okay, for each I, this pi 1I is a conjugate prior to the likelihood n given gamma. Okay, sorry, n given lambda. Okay, and then likewise, okay, we know that this pi 2j, is a conjugate to the PMF or PDF of x given theta. Okay, so this is standard. Okay, so our goal here would be to try to put the pieces together, okay, to introduce dependence between lambda and theta. Okay, so our original motivation, okay, would be that, for example, I think Bin and others, they have talked about the example where the claim number is Poisson, right? And then we know that the gamma would be a conjugate. Okay, so for example, if you look at the individual claim, if you assume, for example, exponential or gamma distribution, okay, then we know that the gamma will be a conjugate as well. Okay, so the thing motivates our work would be that, okay, if I propose this bivariate conjugate prior on the lambda and theta, let's say if I assume Poisson claim number and the exponential claim amount, okay, then the gamma, then the pi 1i, if the pi 1i is assumed to be gamma, pi 2j is assumed to be gamma as well, then we know that, right, these are the conjugate for the both of the likelihoods. Okay, then these guys, okay, would look like some kind of mixture of gamma distribution, okay, which would have nice property, and this will form a bivariate conjugate prior. Okay, so of course, right, when I mentioned Poisson and exponential, okay, that is just for you to this is just an example. Okay, of course we can keep things general here, okay, with the distribution of x and n being in the exponential family. So in this bivariate conjugate prior, we have the weight here, alpha ij. So of course, the sum of these alpha ij's should be equal to 1 in order for this pi lambda theta to be a proper joint density. Then of course, we actually would allow some of the alpha ij's to be negative. Okay, so this would be still fine as far as the results are concerned, as long as the pi lambda theta is a valid bivariate density. Okay, so this type of joint distribution has been used in other papers such as Philbon and Wu, and my own paper with JK as well for other purposes. And then we know that if this alpha ij can be represented as, let's say, alpha I and times maybe alpha j, for example, then you can factorize this joint density, and then in that case, lambda and theta would be independent. Okay, then if the set omega only consists of one element, then of course, right, we will also retrieve the classical univariate case where the conjugate prior is just the one that corresponds to the linear exponential family. Okay, so we have the general results here. So under our proposed bivariate conjugate prior, we can derive the bivariate posterior PDF, okay, given the past claim history. So we can see that given the past claim history of the claim number and individual claim amount, the posterior is still of the same form as the prior, apart from the fact that you need to update the weights alpha from alpha to alpha star, and then you need to update the pi 1i to pi 1i star, and you update the pi 2j to pi 2j star, okay, with always updated parameters, including the mu's. Okay, originally in the prior, right, we have the mu and the k as the parameters, then we need to update this as well. Okay, so this is the result on the bivariate posterior, and then here are the specifics of the updates, and then we see that the updated parameters do depend on the total number of claims in the past and the total claim amount in the past. So the proof of this is fairly straightforward. Okay, the proof starts with the fact that if you look at the bivariate posterior, we know that this is proportional to the likelihood, and then basically we just plug in all our assumption and then try to normalize, and then figure out what the components, okay, what the components of the renormalized density are. Okay, so predictive joint distribution. So our goal, okay, one of the reasons why we want to find the posterior distribution of the theta and lambda will be that way we want to project the total claim in the next period. Okay, so we will have some notations here. So we denote x substitute by t+1 to be the vector of the claim in the next year. Okay, then of course the number of claim in the next year is uncertain. Okay, so that would be denoted by n of t+1. Okay, so we are interested in the predictive joint PMF or PDF, okay, of the number of claim in the next year, and then the individual claim amounts in the next year, given the past data. Okay, so we can show that this predictive distribution, okay, can be written as the following integral. Okay, so you have essentially you have the likelihood of the claim number in the next year and the individual claim amount in the next year, but you need to integrate this respect to the posterior distribution of the risk profiles, lambda and theta. Okay, so we can show this to be true. Okay, and then of course, right, you may say that well, the previous results with regards to the predictive joint distribution is with regards to the claim number and the individual claim amount. But of course, right, the item that concern us the most would be the aggregate. Okay, what would be the aggregate in the next year? Okay, so we can use our predictive joint distribution, okay, to find the predictive joint distribution of the claim number and the aggregate. Okay, remember the previous result is the joint of the claim number and the individual claim amounts. Okay, but now we would like to use this to find the joint of the claim number and the aggregate. Okay, this is the aggregate in the next year. Okay, so using the previous result, okay, we can show that such predictive joint distribution can be written as this integral, okay, where we have the f x given theta star bracket m. So this is the m-fold convolution of the distribution of the individual claim amount. Then of course, if we assume specific distribution for the n given lambda and the x given theta, and then we know that, right, we can find the posterior distribution pi, then we can plug in everything and then to find some nice results. So that is the case if we assume specifically the bivariate mixed Erlang prior distribution. Okay, so so technically we will need the assumption that, okay, we will need this assumption with regards to the ratio of the pi star and the r prime. Okay, so this assumption typically appears in textbooks like loss models, and then when this holds, typically everything will be equal to 0. Okay, so essentially what we need is that here the lambda underscore and the lambda overscore, that these are like the endpoints of the domain of the prior distribution of the lambda, and then likewise for the theta as well. So essentially this lambda underscore is 0 and the upper limit is infinity. So essentially when this holds, typically both sides are 0. Okay, so this is a technical assumption that is typically satisfied. And then in this case, the Bayesian premium can be shown to be of a like a linear sum, okay, with the weights, with the updated weights alpha ij star, okay, and then multiply this by the mu 1i star and the mu 2j star. Okay, so it's very neat. Okay, and then we know that the mu star, okay, can be expressed in terms of the original mu's and also the total claim number in the past and the total claim amount in the past. Okay, so if we assume the bivariate mixed Erlang prior, okay, then we will use the Poisson likelihood for claim number, and then we can use the exponential likelihood for the individual claim amount. Okay, and then according to our previous results, okay, so we know that, okay, the Erlang distribution would be the conjugate, okay, for both Poisson and exponential. So that in fact a mixed Erlang, okay, a mixed Erlang type of the prior, okay, would be conjugate, okay, to this bivariate model. So in this case, okay, we can see that the bivariate posterior is still a mixed Erlang distribution with updated weights, okay, and then with the updated individual Erlang distribution, okay, and then we can calculate the Bayesian premium very nicely, okay. But more importantly, we can do a bit more, okay. We can do a bit more, okay. Not only about the joint distribution of the claim number in the next period and the total claim in the next period, due to the fact that, for example, if we go back and look into the this joint distribution, right, we require the f star m, right, that is the convolution of the claim amount. So if now with the claim amount being exponential, we know that the m-fold convolution itself would be an Erlang m distribution, okay, and therefore we can obtain the very nice explicit results here. Okay, we can evaluate the integrals that we have in the general formula to find this nice result with regards to the joint of the claim number and the aggregate claim in the next year in terms of negative binomial distribution and generalized Pareto distribution. Okay, and then we can do even a bit more with regards to the predictive moments, okay, which usually are not calculated when we are just concerned with Bayesian premium in the traditional textbooks. Okay, so but now we not only that we know the Bayesian premium, we also know we can calculate the second moment, okay, which would be important because that will give us the predictive variance. And of course, can imagine that, right? If two policies have the same Bayesian premium, okay, then if they have different variance, then actually I think you should charge a bit more to the policy that have a higher variance, okay, using, for example, like standard deviation premium principle or variance premium principle. Okay, then not only that, we can also calculate the joint moments of the n and the aggregate in the next period. Okay, and that will also lead to, for example, things like the predictive covariance of n and the aggregate. Okay, so I'm a bit running out of time. So anyway, so I would just like to quickly mention that we also have other, okay, we do have other examples of bivariate prior that falls into our that belongs to our assumption. Okay, there are special cases of our assumptions. Okay, for example, we can assume like a bivariate gamma mixture that is still that would be the conjugate, right, to the Poisson claim and the exponential or gamma Poisson claim number, okay, and the exponential or gamma individual claim amount, okay, and then we can also use the FGM copula with Erlang marginals as a prior, okay, then that also can be proved to be a special case of our prior, okay, and then we can also use a bivariate beta distribution as our prior, and then that would be the conjugate to a binomial or negative binomial claim number, and at the same time binomial or negative binomial individual claim amount as well. Okay, so I think I should stop here. I don't think I have time to go through the numerical results, but I will refer you to the published paper in IME if you are interested in the numerical results. Okay, so basically in the numerical result, we can show that when there's dependence in the prior distribution, then there is really quite significant impact on the Bayesian premium and the predictive variance and predictive covariance as well. Okay, so it's important to take dependence into account, especially when we don't have sufficient data. For example, when you have a new policyholder or a policyholder with just limited years of experience, so that would so dependence will significantly impact the Bayesian premium and so on. Okay, so I just stop here. Thank you.
Thank you very much. Any questions to Eric?
So I have just a quick question. So here, to incorporate possible dependence between the number of claim and amount of claim, so you assume that the prior distribution is a mixture of, finite mixture of, product of prior for n and prior for x, right? Yes,
of course. Well, to interpret things easily, right? Then we may assume it's like it's mixture, but of course, right, it can be a combination, right? By combination, we mean some of the alphas can be negative. And then, for example, in our example where we have like if the prior is a FGM copula with Erlang marginals, then we can show that some of the weights alphas are negative.
I see. Thank you.
Yeah, but of course, if you use a mixture, then maybe in terms of estimation, it will be easier, right? You can use EM algorithm and so on. Yeah.
Other questions? to Eric or to other speakers? All right. It's been a very good session. Thank you very much for participating and for your wonderful, very nice talks. Thank you, Claudia, for hosting.
Well, thank you everyone for coming and great talks.
Thank you.
Thank you again, Dan. Yeah.
All right.
Thank you.
Good.
Very
Good
nice
to
to
see
meet you
everybody.
all.
Yeah,
Yeah,
Thank you.
bye-bye.
safe everyone. Bye.
Bye-bye. Bye-bye.
Bye-bye.
Bye.